Hello. So far we've done vectors, we've done arithmetic. Now it's time for the interesting parts of complex numbers. The most important thing I reckon about complex numbers is that, these vectors don't have to be represented as coordinates. In fact, a lot of geometric features are not so well represented with Cartesian coordinates. Have a look at this vector, for example. We're starting from over here to there. Now this point can be anywhere, as we know from vectors. The most important thing about this vector is that it's an arrow. It goes from here and ends there. Okay? It obviously travels a certain amount of distance and it goes in a certain direction. Now if we were expressing this as a coordinate, we would say that the real part of this complex vector is root 3 and the imaginary part of this complex number is 1 plus 1. So what actually happens then is that this complex number can be represented by z equals to root 3 plus I. Okay? But the same vector can be represented in a much more intuitive way. Okay? And this is the other way. This is called the polar form, or in most textbooks we will call it the modulus argument form. Now the words modulus and argument have very specific meanings. The word modulus is basically how much quantity you have traveled. If you were traveling on the map and you go from here to there, then modulus will be the distance that this vector covers. Okay? Now the way we demonstrate modulus will be using the absolute value symbol, but this time we read it as modulus of z. Okay? Now in this particular vector, we know that using Pythagoras, the modulus of z will simply be 2. So we will say that will have a modulus of 2. Okay? Now we would still label this vector as z. I'm just showing you that the modulus of this vector is actually 2. On the other hand, what about its argument? The word argument stands for the angle, starting from the positive real axis, or positive x-axis if you like, and going anti-clockwise. The same thing as you would do if you were doing all stations central in 2-unit mathematics. So going from here to there, we know by looking at this triangle that this is about 30 degrees. Now I personally prefer using radian form for this. So pi on 6 radians will be the amount of angle that, that your particular vector is inclined to the x-axis, or the real axis. Okay, so given these two things, it will uniquely define your complex vector, just like your two coordinates would define your complex vector. But this form is so much more useful, as you'll shortly see. Now there's two different definitions for argument. There's one called principal argument, and there's one that you can use for any angle. As we can see, we could have said this is pi on 6, or we could have went all the way around like this and said this was 13 pi on 6, because we know that 2 pi is a complete revolution. So why is pi on 6 more desirable? But besides just looking simpler, that's what the principal argument is. When you talk about the principal argument, you use capital letter arg, okay, and we're talking about the argument of z, okay, and this ranges from negative pi to pi, inclusive for pi, but not including negative pi, because we know these two are the same spot, they're the same direction, so we prefer to keep the positive pi. And any argument we just simply write as argument of z with small letter a, and this stands for any angle you like. As you can see, an argument of 13 pi on 6 is really the same as an argument of pi on 6, because they do point in the same direction. Okay, and the way to write the actual complex number will be z equals to r bracket cos theta plus I sine theta close bracket, or abbreviated to r cis theta. Now you might think, well, how do we actually know this? What is r cos theta? And if you were to expand it, what is r sine theta? Well, r cos theta is the real part and r sine theta is the imaginary part. And this is quite simple, because r here is the modulus of z, okay, sort of like the radius, so to speak. And if you have that, then if you want to find the x coordinate, or the real part, you'll simply just use the cosine ratio. And if you want the vertical part, you would use the sine ratio, and that's what we have here. Okay, so going from this diagram to that diagram, we would try to find the angle, which we'll discuss later, and going from the modulus argument form back to the Cartesian form or the algebraic form, you will simply expand this out and find the real and imaginary parts. Right, now this is a really important skill here, the idea of finding the argument if you were given the complex number. Oh, by the way, the diagram we showed above in our example was 2 cis pi on 6. And that's how you write it. Okay, now to find the argument given any sort of complex number, such as z equals to minus 1 plus root 3i, or anything else, the key here is to know it via diagram. Okay, you must be able to visualize where this is. Okay, what point on the argument diagram represents z? And the easiest way to do that is to draw a diagram. So minus 1 plus root 3i. Now generally, if we want to find a point that represents z, we would just start from the origin, okay? Because then if we go minus 1, we'll go that way, minus 1, and we'll go up because it's positive root 3. And this vector, going from the origin to that point, this vector will be obviously z. Now, knowing that vector, we must again consider its modulus and its argument. Now, the modulus is easy. It's just use Pythagoras, and we can find it quite easily. So modulus of z equals to, that will be 1 plus root 1 squared plus root 3 squared square root, and that gives us 2. Okay, and the argument is going to be this angle. As you can see, this angle is in the second quadrant, so we know the angle should be obtuse. But if you were doing some fancy thing with tan theta equals to root 3 on minus 1, what you're actually going to get when you press the shift tan button is that you're going to get a negative answer of, I believe, pi on 3. Now, if you think about this, this is the fourth quadrant, but that's contradictory to our diagram. Whenever in doubt, the diagram is always right, and your algebra, it doesn't capture the meaning of it. So this is completely wrong. Okay, and your goal is to not use tan or inverse tan to straight away find your argument. You simply use inverse tan to find the acute angle. Just call it alpha, the acute equivalent. And that's root 3 on 1. Okay, and that gives us basically pi on 3. Now, given that acute angle, we simply need to find in the second quadrant the actual argument of z is going to be 180 or pi minus pi on 3, which is really 2 pi on 3. Okay, you don't have to use a letter alpha if you know what you're doing. You simply have to go, yep, the acute angle, we found it, and we know now what the argument is based on the diagram. So to conclude, this particular complex number, minus 1 plus 3i, can be rewritten as 2 cis 2 pi on 3. Okay, and the steps to doing this is to find the modulus, obviously, using Pythagoras, and then finding the acute angle that these numbers give you. Okay, this is sort of like the y and this is the x, so you go root 3 and 1. And then finding the actual argument from the diagram. Now, try the questions at the end of this video.